Okay, so we're going to continue with our example here, 5.8. We are going to solve for our mass of the rock. So the weight is 180 newtons, and our gravity is going to be 9.8 meters per second squared. Okay, so let's go ahead and put that into our calculators. And we get 18.4, and this is kilograms. Okay, so this is the mass of our object, of our rock. Okay. Now we need to, from this diagram, determine an equation. So we had that F net equals the mass times acceleration equals our sum of the forces. Oops. Okay. So we have a positive force in the y direction. Okay, and then we have our weight in the negative y direction. Okay, so this is going to be our setup. Now we want to solve for our force here. So our force is going to be equal to mass times acceleration plus the weight. Okay. So our mass is 18.4 kilograms times our acceleration is 1.5 meters per second squared plus our weight, which is 180 newtons. So we plug that into our calculator. We get the force is 208 newtons. Okay? So this is the force that he has to lift that rock. Okay? Alright, so let's move on to Newton's third law of motion. When one body exerts a force on a second body, the first body experiences a force that is equal and opposite in direction to the force that it exerts. Okay? Basically, it's saying that there is an equal and opposite reaction to any action. Okay, so if we say that this person is running, the runner is pushing on the ground, and the ground is pushing back up on the runner. Okay, it's kind of an interesting, kind of weird concept at first, but hopefully through examples we will be able to understand it better. Okay, or we have this person swimming. Okay, she's the system of interest. Her feet push on the wall. Okay, and the wall pushes back on her feet. That's why these things don't move. Okay, and then we have the direction of acceleration here. Okay, mathematically, the force of A onto B is equal to the negative of the force of B onto A. Okay? Alright, so let's go ahead and do an example. Okay? So this states a physics professor is pushing a cart of demonstration equipment to a lecture hall. Her mass is 65 kilograms, the cart's mass is 12 kilograms, and the equipment's mass is 7 kilograms. Calculate the acceleration produced when the professor exerts a backward force of 150 newtons on the floor. All forces opposing the motion, such as friction on the cart's wheels and air resistance, total 24 newtons. Okay, so we want to find the acceleration produced when the professor exerts this force. Okay, So we're looking at system 1 here, and they were kind enough to draw a free body diagram for us. Okay, we are only interested in everything that's in the x-axis here. Okay, so we have F net equals mass times acceleration equals F floor minus F. Okay, so this is the equation we're going to use. And we want to know the acceleration. So we're looking for this guy here. Okay. All right. So she is exerting this backward force of 150 newtons. So that's what F floor is. And F, our frictional force, is 24 newtons. Okay, so we have mass times our acceleration, which is unknown, equals 150 newtons minus 24 newtons. Okay. And our mass is going to be the total mass here. So our mass is going to be 65 kilograms plus 12 kilograms plus 7 kilograms. Okay. So let me quickly put that into my calculator. Oops. And we get the mass is 84 kilograms total. Okay, so let's take that down here. So our acceleration will be 150 newtons minus 24 newtons divided by 84 kilograms, or it's going to be 1.5 meters per second squared. That is our acceleration. Okay? All right, so in this next example, it's related to the last one, and now we want to know the force that the professor exerts on the cart using the data from before. So we are now looking at this force here that she is exerting on the cart. Okay, and we will be looking then at system 2 here. So we are only looking at the external forces on the cart. Okay, so we have professor force here and the frictional force here. Okay, and it has it here in the free body diagram as well. So we're going to do a similar thing. So F net equals mass times acceleration equals the professor force minus the frictional force. Okay. And our acceleration will stay the same. Okay, so we have 1.5 meters per second squared is our acceleration. Okay, so let's note that. Our mass is going to be different because we are now just looking at the cart's mass. So it's going to be the cart's mass plus the equipment's mass. So 12 kilograms and 7 kilograms, or 19 kilograms. Okay. And our frictional force stays the same, that 24 newtons. Okay. I'm going to go ahead and write that down so we don't forget. All right, so F professor is going to equal mass times acceleration plus frictional force So we have 19 kilograms times 1.5 meters per second squared plus our frictional force. Okay. 19 times 1.5. Okay, and we get a total of 52.5 newtons. So this is the force that the professor is putting on the cart. Okay? Alright, so this is something that we've been kind of hand-waving over. It's something called the normal force. Okay? Now, the normal force is the force that is supporting the weight of some object or load and is perpendicular to a surface of contact between that load and whatever is supporting it. Okay, so say we have a bag of dog food called Bow Wow Chow, pretty inventive, right? And we put that onto a table. Okay, the table doesn't just collapse or anything, right? It doesn't just move out of its way. The table now puts a force that opposes that weight of the dog food. Okay, so that's what this normal force is doing. It is supporting the weight of this object. Okay, and how you calculate it, the vector of the normal force is equal to negative the mass times acceleration due to gravity. Okay, so it is equal and opposite to the weight of an object. Okay, so let's put that to use now with an example. Consider this skier on a slope. Her mass, including equipment, is 60 kilograms. We first want to know what her acceleration is if friction is negligible. So friction is 0 in this first case. Okay, so what we'll do is we'll break this down, this diagram here down, and find her force first that's going downhill, and then her acceleration. Okay, so F net is equal to mass times acceleration. Okay, and we just want to know her downhill force, right? So this will be, since we have our coordinates set up in such a way, we can just look at our x direction here. Okay, so our F net equals equals MA equals, it's going to be WX. Okay, and our friction is negligible, so we don't need to worry about that part yet. Okay, so her mass, we know her mass, so we just have to solve this now. WX over M. Remember that W is M times G, okay? And we are looking at WX, so to get our X component here, it'll be opposite over hypotenuse, or the sine. So we have mg sine theta over m. Okay. Or, since our masses would cancel, 9.8 meters per second squared times sine of 25 degrees. And we get, we'll find that in the next video.